Welcome back, guys. Today we want to start looking at pathfinding algorithms, and today we're going to be looking at Dijkstra's shortest path algorithm. To help us out, we're looking at a map for a very popular game, which I'm not going to say out loud. In this game, our player CJ is stuck in the wrong part of town, and he needs to get back to Grove Street before he's discovered by the Vigos gang. So, how do we use pathfinding algorithm in specific Dijkstra's to find the shortest path to where we need to get to, which is from here down to Grove Street over here. So thanks to law enforcement, CJ has been dropped off at point A and he needs to get back to home to point G, aka Grove Street. In 1956, Dijkstra devised an algorithm for finding the shortest path from Rotterdam to Groningen. Dijkstra's algorithm uses weighted paths to work out the shortest path. So as you can see from the legend on the right, a node represents a location that can be visited, and the dotted lines represent paths, which can be called edges. These have a cost. The aim of the shortest path algorithm is to get from starting point to the destination with the least cost. So we calculate the shortest path by visiting connecting nodes from the starting point. We plot the cost into a table, and since we don't know the calculation of the distances as yet, we label them infinity in the table for now. We first visit point A. This is our starting point. This has zero cost because it's where we're starting from. So we now look at visiting connected nodes to A and examine their cost. So we work out the cost and update our table. You can see here that our cost is the cost of A and the distance to each node respectively. So the cost to C is 0 plus 5 equals 5, and the cost to B is 0 plus 3 equals 3. And now that we have looked at all possible paths from A, we're not going to be visiting A again. So what we can do is we can mark A in our visited nodes list. We now need to move to the next unvisited node that has the shortest known distance. The shortest path or vertex from A was to B, so we're now looking at B. The possible paths or vertices are to either C or D from here. So first, let's look at B to D. The path from B to D has a cost of 3 plus 4. We can see here that the distance is 3 plus the distance here, which is 4, equals 7. And so we update our table here with the cost of D being 7, and we also update that the previous node to D was B. So now we can look at the cost from B to C, and we know that the distance, the cost of that is from here, is 3 plus 7, which equals 10. Now in this case, we don't need to update the table because the cost of getting to C was already updated when we looked from the path of A, and because this path is less costly, we don't update it. So we only update the table if the cost is less. So in this case, it's at a lower number at 5, and 10 is a higher number, obviously. So we leave that as it is and we don't update the table. So now we can say we visited B and we won't be coming back to it. So we've added B to our list of visited nodes. And now we look at the node with the shortest distance from the start that hasn't been visited. And this is C. So from C, we can see that the possible paths are to D and E. So if we do the same kind of calculation again, we can see that the path to D is going to be 5 plus 3, which is 8. But we can see that the path that we have to D already, if we were coming from B, is 7. So again, we don't update the table here. So the path to E is going to be 5 and 5. And this doesn't exist in the table yet. So we've now added 10 to our table. And we've said that our previous node to E was C. So we have now visited C. And so we can update our visited nodes list. And we can see that the shortest unvisited node from C is D, and the unvisited node from here is E. When we calculate the path to E from D, take into account the shortest path to D the path is now 9. So as you can see, if we were to take this path, 3 plus 4 equals 7, plus 2 equals 9, that leaves us with a new updated path for E here. So now what we do is we update our value for E because we have a shorter path, and we also change the previous node from C to D because this is a shorter path to E. We can now also update our visited nodes list with D. So finally, we are now visiting E, and we can state that E has no unvisited connected nodes. So that means that we can actually also mark off E as now having been visited. So that completes our table. And by doing this now, we should be able to say what our shortest path is from A to E. By working backwards, well, we know that to get to E, the shortest path, the shortest distance is 9. So working backwards, we can say that to get to E, we have visited from D. From D, we came from B. From B, we came from A. So I've tried to condense this into 4 simple steps for us. So while our unvisited node is more than 0, we can say then that we need to visit the unvisited node with the shortest distance from the start. We need to calculate the distance to its connected unvisited nodes. If the calculated distance to a node is less, then we update the table with both the new distance and the previous node that we visited from. And lastly, we add the current node to the list of visited nodes. And this brings us back to the problem that we began with, which is helping CJ through Los Santos from point A to Grove Street. So I've added this to a worksheet actually, guys. So go to the website as always, download the worksheet and see if you can find the shortest path to help CJ get home. With that said, I'll see you guys in the next video where we explore another topic.